of positive integers. And guys, I'm going to use a symbol here. C is for integers. I'm going to put a little superscript of a positive to indicate there, here this function has only positive integers, not the entire set, for its domain. A function whose domain is a set of positive integers. That's the definition. When I first saw that definition, I think I knew what a sequence was. When I saw that definition, I thought, wow, maybe I don't know what a sequence is. Short definition. Let me go back to your first example there. I went back and want to use the 2, 4, 6, 8. As I have here. Look at this sequence, guys. This is a sequence. Now, can anyone give me, here's goes the first part. By definition, can anyone give me a function that's called f of x right now? That might be the function that these numbers belong to.
Previous number plus.
Yeah, no, I want a formula. Okay, I heard what now? We want f of x, let's call it f of x. Okay, right here on the side. F of x equals, I heard something, what was it?
2x.
Well, could it be just this? 2x. Now, Selena, by restriction, though, they're saying if you write a function to represent this sequence, which we think is 2x, or with my help there, the restriction is the domain, the x, the domain, must only come from here. And by the way, guys, a set of positive integers, they're talking about numbers like this, no fractions. These are the only numbers you can use for the x, the domain, in a sequence. You cannot use negative. Now, if I go up to this and replace x by 1, right here, would I get my first term?
Yes.
If I replace x by 2, which is allowed, in what I think the function is, 2 times 2, would I get 4? If I put a 3 in there, would I get a 6? A 4 in there, would I get an 8? So I can use that as my function, and I've restricted the domain to those positive integers. And that will give me a set of numbers. I see it there. Okay? Now, can someone tell me, I did this one. This is a set of odd. Boy, I've got to be very careful here. This is a set of odd. Does anyone have in mind, be careful, and we'll test it, a function that might satisfy this sequence? Got it? Yes?
2x minus 1.
Look at this, 2x minus 1. Hang on. I'm going to check. Let's replace x by 1 first, by restriction. If I replace x by 1 in the formula given to me, 2 times 1, then minus 1 gives me a 1, which is the first term. If I put a 2 in there, by restriction, 2 times 2 is 4, 4 minus 1 gives me a 3. Put a 3 in there, 2 times 3 is 6, 6 minus 1 gives me a 5. Is that formula sure enough that those restrictions give me those numbers? That's all we're looking for. And that is a sequence by definition. A function whose domain is a set of positive integers. And that's what this chapter is all about when I move on into it. Now, I did this before I stuck that handout. Here we go. On the side here, I'm going to give you another sequence. Looks like this. We'll make it infinite. And I want someone to look at it and name what you think the function is for this one, for this sequence. That will give me those terms. Oh, I see a hand went up already. Yes?
X squared.
Look at that. F of x equals x squared. And for a check, place x by 1 first always. You get 1 squared 1. Put a 2 in there, 2 squared is 4. Put a 3 in there, 9. That's it. That's the function. Now, PK. When they're talking about a function for a sequence, they use a different notation. They get away from the f of x, g of x, and h of x. They call it a subscript n. Rather than f of x, a subscript n. in this case, it's giving me what, x squared here? So we're gonna call this x squared, n squared. Something like that. So they use a little bit of a different notation, actually meaning the same thing though. They love that a subscript n for a sequence. Now why do they change from f of x, g of x into this? This now says, look at this in the purple, a subscript 1, my first term, should be equal to 1 squared, which is 1. And if I look back, yes, there it is. The second term, written like this with this new notation, a subscript 2 indicates I want the second term. Put a 2 in there for the n. 2 squared is 4. Looking back, yes, that was my second term. Is that true, guys? Now, if I want, with this new notation, what is the value for the 50th term? Written as a subscript 50.
1,500.
Yeah, put 50 in, 50 squared. And I think I heard, what, 2,500?
Yes.
And that's the way it works. The only thing you have to accept is a little different notation. But we're still talking about a function here. Okay, well, something else in before I jump into the handout. So we're gonna help you out with this one. Lead you into something here. I got, oh, beautiful. 1, negative 1/2, 1/3, negative 1/4, 1/5, so forth and so on. Everything's copied down correctly. And I need a function for this one, and I won't start using that notation. In other words, I need an a subscript n function that would give me those terms.
It's 1 n plus 1.
Wait, let me get that.
Negative 1 divided by n plus 1.
Hang on. Now you're saying, you think it's n over n plus 1.
No, I think it's 1 over n plus 1.
Oh, 1 over.
Yeah,
Hang
with
on.
the negative also.
Hang on. Like that,
Negative.
and the negative out here.
Yes.
And we're checking. Here goes. It's supposed to always replace first by 1, by definition. If I put a 1 into your formula, I get 1 over 1 plus 1, which is 1/2. In fact, this is telling me the first term should be negative 1/2. No, that's my second term.
So it's 1
No, I
minus.
know. It is negative 1/2, but negative 1/2 is not my first term. You're close. So I may have to modify what you gave me, or may have to come up with a different formula, but when I replace n by 1, I had better get 1. Replace n by 2, I better get this. N by 3, this. And this one came close.
So it's negative n divided by n plus 1.
Whoa, hang on. Now you're saying n over how much?
N plus 1.
Hang on, and a negative sign out front?
Yes.
Check it. Supposed to always replace n by 1 first by definition. If I replace the domain n by 1 first, I get 1/2 again. In fact, negative 1/2 again.
Why don't you set the first one?
Oh, you want to set the 1 to itself, so you accept this,
Yes.
and then use the formula for the others. Sometimes that will happen. I want a direct formula. Exactly, sometimes it does happen. Does anyone think they know a direct formula? And he is right around it, not quite there. This one's a little bit tougher.
Maybe 2n divided by n plus 1.
Oh, they're guessing. Okay, 2n. Give me more.
Divided by n plus 1.
Okay, well, try it. That should be a negative sign, but test it. If I put a 1 in here, you're going to end up with, looks like 2 over 2. Is that 1? And so what I'm looking for the first term?
But the next one.
No, hang on now. Now if I put a 2 in there, I get 4 over 3. Oh, you're way off on that one. You're say, Professor, is there some, like, formulas like a half angle, double angle formula like you saw before in recapping that I should refer to? Are there some formulas like that here? No, this is based on you, the way you look at it. You got to come up with a formula on your own. Anyone have an idea?
N minus one times.
Joseph?
1 over.
1 over,
No. I think it's N minus one.
something about an n minus 1, where though?
N minus one in the beginning and times,
Wait, hold on. You want negative 1 here, and you're asking me to raise it to n minus 1?
no, I mean just N minus one. Times N minus one.
Oh, out here. Like that.
Yes, like the previous number.
Okay, hang on. I know right now if I replace n by 1, which I must do by definition always, I get 0.
And so we need to divide.
That's not gonna work. My first term is this. No one has given me a formula yet that would give me not even the first term 1. And over here we did it quickly. It was n squared. This was tough. Let me ask you this. Do you think at this point that function notation do you think for sure down here has to be n?
Yes.
Because I know 1 can be expressed as 1 over 1 if I wish. So right here is the denominator, I was just looking at the denominators right now, are those the set of positive integers to begin with?
Yes.
So could I say that must be n? Let n be 1, n be 2, n be 3. That would get the denominator out of the way. It's that top part that bothers me. Now what goes on top? On top I see just a string of 1s.
But there is also a negative.
And it changes signs. Yes.
Is it -1 squared over A?
-1 squared over what I have right now. Right? June,
It's just one.
you saying that? Now that's just merely 1.
We need to negative one times, N minus one.
Not times, you're so around it, you are so
Plus
close.
N minus.
You're so close to it.
Negative one.
You are so close to it.
Negative one raised to N.
Oh, -1 raised to the what, n?
Yeah.
Hang on, Joseph. Now, if I do that, you're getting much closer. If I put a 1 in there, let's test it right now. If I put a 1 in there, I'm supposed to get 1. Put a 1 in there, what's -1 raised to the first? -1. That's gonna give me a -1. You're so close there.
-1 raised to n minus
What you would get?
1. -1 raised to n minus
Hang on. PK, if that's correct here, let me test it. Gotta go back, always put the 1 in first. If I put a 1 in here, 1 subtract 1 is 0. -1 raised to the 0 should be 1. So that would be 1 over 1, will that give you the first term? And then check it out, I got it first. PK, you may have something here. A subscript 1, the first term, with your formula, is -1 raised to the 1 subtract 1 over 1. And we said all this was -1 raised to the 0. And we know that's 1 over 1, 1 checks. Now, it had better work for the second term. A subscript 2, our formula, -1 raised to 2 minus 1 over 2. Don't want to mess up. This gives me -1 raised to what? 1 over 2. Is that -1/2 when you simplify it?
Yes.
Is that what I wanted? PK, I think, I'm gonna test one more. 1, 2, 3, 4. Let's go down to the fifth. The fifth term should be 1/5, if the formula is correct. Let's find A subscript 5. Your formula says -1 raised to the 5 subtract 1 over 5. That's negative 1 raised to the 4th over 5. Guys, is that a 1 on top? Is that 1/5? PK, congratulations, you have the formula. Now, are there other formulas out there? I guarantee you there are, that would satisfy this. We came up with finally one formula with PK's help, right here. PK, thank you so much. There's your formula. And we tested. Looks like it's working. Okay. Now, that's the issue. Now, I know what the final exam will take you so much time to get that final exam done. So when I test you on this on the final exam, I can't give you something crazy. But if you be sitting there for half an hour trying to come up with the formula, well, you could have been using that half an hour to do something else with the final. So I'll keep it reasonable. Okay, I need this one. Turn to what this is all about. Guys, my next one looks like this. I want a function that represents this sequence. We'll make it infinite. My last example. I'm trying to name a sequence. First one, n squared, we got it. PK gave me this beautiful formula, it worked. Not so much about giving me this formula, and when you give it to me, I start testing, when I replace n by 1, I had better get 1. The strange thing is, when I replace n by 2, whoever gives me the formula, I better get 1 again. N by 3, I get 2. N by 4, I get 3. Any ideas? I saw a hand going up.
I was just thinking it's the Fibonacci sequence.
It is. This is a special sequence named for the mathematician who worked with it, Fibonacci.
Can we do the right one by
Hang on, let me give credit to Fibonacci. The Fibonacci sequence. He was doing some type of experiment, you guys can read his history, and he came up with those numbers. Now, we need to come up with a formula, a function for those numbers. I don't think Fibonacci thought about function. He just created the numbers. Anything at all?
Can we take out from one to the previous one? And
Oh, you
times
raised-
something.
Oh, I got you, 2 more.
So for example, the fourth is number 3.
Here. He's telling me, in essence, he said, wait, Professor, I may not come up with a formula right now for you, Professor, but there's a pattern here. And I think he's telling me, if I look at it closely, if I add these 2 terms together, do I get the third term? If I add these 2 together, do I get that term? If I add 2 and 3, I get 5. Add 3 and 5, I get 8. So there's a pattern there in Fibonacci's sequence that he created with this experiment he did. But we need a formula. So whenever, and it may be crazy, when you give it to me, for an example, when I replace n by 1, 2, 3, 4, 5, n by 5, I better get 5. If I replace n by 6, I should get 8. This one's tough. That's the reason I brought it in. I think some students have seen Fibonacci's sequence before and may remember how it was expressed. June.
I think it's a subscript n minus 1 plus n.
Oh, we're getting close. Oh, you're getting close.
Can we say that
Say that again. A subscript n minus 1.
So the previous term. plus-
You're adding the 2 previous terms.
Yeah.
Okay. Now, guys, if I say add 2 previous terms, and she says, Professor, that's exactly what you said to do here. You're going to add these 2 to get that one. Add these 2 previous terms to get that one. So that's involved, and how am I going to represent that? And she's telling me maybe a subscript n minus 1 plus a subscript n minus 2 might represent the 2 previous terms. Okay, hang on now. We test it just with something right now first. Marina, 1, 2, 3, 4, 5, 6. The sixth term should be an 8. If I use what June just gave me, I'm looking for the 1, 2, 3, 4, 5, 6. I'm looking for the sixth term. That would be a subscript 6 subtract 1 plus a subscript 6 subtract 2. This is a subscript 5 plus a subscript 4. Now, 1, 2, 3, 4, 5, a subscript 5 was given to me as 5. And a subscript 4 was given to me as a 3. Is that true, guys? If I add those up, do I sure enough end up with this one, which was 1, 2, 3, 4, 5, 6 was a subscript 6. Does that work? If I take the two previous terms, June, did you have something in mind like this to show that two previous terms are being added? A subscript n minus 1 plus a subscript n minus 2. Looks like I tested right there on that. It works. Except for one exception. Joseph, suppose I ask you to find a subscript 2, which is 1. And I use her formula. Here goes. How does that look in her formula? She says a subscript what? 2 minus 1 plus a subscript what? 2 minus 2. Which is a subscript what? 1? And this one looks very strange. That's a subscript 0. Nope, I don't think I have an a subscript 0. So what June has given me is a big, big, big benefit. But it's not going to work always. It worked here, but not always. Here's what they do, just sort of close this down. I think our student tell me, says, Professor, if I run into a difficulty, can I go ahead and say, please accept these two? And then her formula will work after that. Is that true, guys? If I had 1 plus 1, do I get 2? So if I go ahead and say, please accept that the first term is 1, the second term is 1, and then use June's beautiful formula. In other words, like this, A1 is 1. You said equal to 1. A2, the second term, also 1, Professor. Then her formula could be written like this. And let this be the complete formula. Therefore, if I ask you out to write out Fibonacci's numbers, you'd say, well, Professor, you already given his first term is 1. It was. Strange thing about this sequence, the second term is also 1. It is. And then that from that point on, use this formula. Let's try to find a subscript 3 with June's formula. A subscript 3, the third term is 2. If I use her formula, a subscript 3 looks like this. A subscript 3 subtract 1 plus a subscript 3 subtract 2. And that's a subscript 2 plus a subscript 1. Now what is a subscript 2? We set it at 1. Plus a subscript 1? Also 1. We set that. Add them up, I get 2. Looking back, yeah, that's my third term. Whoa. Rena? So Fibonacci, I don't know where the Fibonacci thought about this formula. He was going to experiment with this to get these numbers. That's what his concern was, how to get those numbers to begin with. We came up with now a formula. Okay.
So we can write n is greater than or equal 3.
Oh, look at this. Look at this. You read down here. This her formula works only for. Okay, you saying this? From the third term on. Is that true? We set the first 2 terms. Beautiful. So we're going to put that restriction on June's formula. That formula will work from n is greater than or equal to 3. Nice. That's true. Okay, guys. Now that's what sequence is all about. Now, am I going to give you something crazy where you have to sit there for half an hour and try to come up with a formula, waste time, where you could have been spending your time on the piecewise function on the final, or could have been doing a logarithm function on the final? No. I'm going to go crazy on you. We'll be tested somehow on Guys, can step to the side. Took a little time here though. Now you sort of get a sense of what's going on? Sequences? That's all that's going on. We'll actually write the sequence with this restriction. Okay? Now, I've got just a few minutes. I'm not gonna do much and then we'll take a break. Guess what comes up next in the next section? After they think students have enough now to deal with the sequence and know what a sequence is, guess what they ask us to do? Here goes.
Geometric sequence.
And here it goes. And I'm gonna stop and we're gonna take a break. Chapter 11 is gonna be beautiful. Here we go. Everybody should do this. Take a sequence, I'll take one of the most basic ones. Take your sequence. And this time I'm gonna stop at 100. For a reason. That's the sequence. Philip, class, this is what we'll be doing after the break. Now they're gonna say, beautiful, take that sequence, but now do this to them, to the terms. Add them.
Not just
Don't
sum.
try to find the term. Add them up, you get a grand total.
Summation.
Thank you. And they use a symbol here, and I'll get into this when we get back from the break. The Greek alphabet, sigma. Summation. So I see that, and I'll show you how to use it after the break. I just want to tell you a little short story here about this. We're using a summation symbol for a sum. Now, here's the story. Based on truth from what I've read in history of math. I think Santa Monica always needed a history of math class. You guys really enjoy that. Not working math and solving problems, but reading the history of math. Where did all this stuff come from? This came from something. The story goes that one of the famous mathematicians, when the story that I read placed this mathematician, Mr. Gauss, and you guys who may do physics or chemistry, you may have heard that name before. Mr. Gauss, at 7 years old, this is what the story goes. He was 7. And they noticed how smart he was out there, off the spectrum. 7 years old. So they paired him up with another mathematician at that time, and let that mathematician be his mentor. And when they first met, the story goes, whether it's true or not, the story goes that Mr. Gauss, at 7 years old, was asked by the mentor, add these up and give me within seconds the sum of the first 100 positive integers. And Mr. Gauss, at 7 years old, not that high, I guess, raised his hand to the mentor. The mentor thought, oh, he's got a question. He doesn't not know quite what I want. No, he had the answer. Had the answer. They say within seconds. Now, at 7 years old, would I have been that clever? No way. But I didn't even know how to spell math. 7 years old. Does anyone have an idea before we close down what Mr. Gauss did? Clever. And he got the answer. And he used a little common sense.
Plus 199.
Hang on. So he thought to himself, exactly. He said, wait, mentor, could I not get the same answer if I did it this way? Should you get the same answer? You get it backwards? He was smart enough to recognize that at 7 years old. Then he thought, oh, wait. You gotta keep in mind, this way, there was no calculators around. Everybody did math with rocks or something, I don't know. But he does something like this. What do you notice, the way he has everything paired up? I think all those pairs add up to what, 101? And he was asking to do this, what, 100 times, add the first 100? So in his mind, he says, oh, I need 100. Okay, 100 ones.
So it's the final one.
But, he said that's when I actually add twice. So what do you do to compensate?
The one was.
7 years old. Yeah, cancel a little bit. And 50 times 101, I think is 5,050, is it? And there's the answer. Now, before we take a break, one time I was teaching the class here, and we were talking about this. And the student was watching what I was going to do here. They said, really, sum of the first 100 positive integers, we add them all up, is 5,050. Yes, Mr. Gauss showed me how to do it. Then I heard a clicking sound. One of my students had a calculator out. 1 plus 2 plus 3, how's that right? That was plus 4 plus 5. He was going to confirm Gauss. He's going to add the first 100 on the calculator. No. This is 5,050. Guys, any concerned about what Mr. Gauss did?
It's like,
Now, would I be that clever? No. No, I doubt it. To know that you can add backwards. You do something to get the answer. Okay, that's what we'll be doing. Summations when we get back from the break. Guys, any concerns? I think you're well deserved 15-minute break.